Hey everyone, my name is Bedros Janoyan and I'm on Cornell Autonomous Underwater Vehicle and I'm going to be talking a little bit about our hull design. So our overview of our UHPV upper hull pressure vessel, it basically provides a watertight enclosure for the electronic racks, the PCBs, and all the cameras and sensors which might be integrated inside of it. It also provides a place for external components to sort of be centrally routed to that central PCB via SEACON connectors, which are underwater sort of cables. So this is like a funny infographic that we made one year that has each member sort of next to their project and shows basically, the racks are the structure that support the PCBs and they're within the UHPV. And then there's the SEACON connectors, which I talked about, which go and sort of like branch out to the various locations of the other enclosure. So kill switch, torpedoes, droppers, etc. So some constraints and objectives from year to year. We always try to make it seal securely and consistently, which is just important for any underwater application. Securely mount to the frame, provide mounting for all SEACON and internal and external adjacent structures. The number of SEACON sort of changes from year to year depending on what we include on each vehicle or what we include inside the UHPV. But some objectives, easily removable hulls, could be one hull, could be two. Easily machinable since we do everything in-house. Easy to access the commonly used SEACON and minimize size and weight. So generally, sort of the design follows pretty similar stuff from year to year for good reason, which I'll go through, but it's usually consisting of like a mid-cap portion, which is like here, or just a single cap. Then all of them have these hulls, which have a collar and an end cap. So hull, collar, collar, hull, hull, end cap, collar. And also there's also these like SEACON panels, which have those spots for the SEACON so the wires can branch off to various locations on the sub. In this iteration, there was a camera included. This one, the camera was also included, hence a clear end cap. But then you can see in these three, actually, the cantilevered racks and computers are here as well. So transitioning to CAD, I loaded up our most recent vehicle here. Let's see. So you can sort of see the context in which this UHPV sits. So it's mounted in the back. These two tabs, these two sort of kind of hard to see, but there's two things that kind of brace from the back. Oh, I zoomed out. You can see the SEACON panel here, pressure relief valve, cantilevered rack system. And then there's a camera here, and then there's these tabs which secure it in the front. And so this whole red portion is free to slide. The red and translucent portion is free to slide in and out and be mounted on these tabs. So the racks always stay in place on this back black part. So I can open up this one just to show more specifically what we've got. So we have like, let's see. So here's the computer, here's the cantilevered rack portion, pressure relief valve, SEACON, call this the cap, collar, hull, end cap, and camera. You can see the camera in this iteration, let's see if I can, is mounted on a bracket. So the camera is not there modeled right now, but there is a bracket that sticks out of here and it provides a mounting spot for the camera. So that means one less SEACON coming out of the side because the wire can go directly to the back plane. So just to go over the parts briefly, the mid-cap / cap is basically the largest structural component. It holds a SEACON panel, interfaces with the hulls, collars, supports the racks. In some of these big versions, took about 100 manufacturing hours and 50 sanding hours. So from year to year, if there's a part being reused by us, it's probably going to be the mid-cap. It's always made of aluminum 6061 T6. Just to hit tolerances, we do everything in-house. So cheap and easy to machine, basically. The hulls are made of just acrylic tubes. They interface with the collars and the end caps. They're clear, helps us see the electrical boards without like taking everything apart. The biggest challenge with these is since they're thin and not easy to machine reliably, we have to interface metal to create meaningful seals to interface with other metal parts. So I'll go through that quickly here, but the end cap is sort of just the part that has the tabs on it that's secured to the frame. And we actually do epoxy right here. So there's an adhesive that makes a watertight seal and makes this portion one entire unit. And there's also commonly weight savings or heat sinks depending on year to year. that are put on the front on this side. So the collar is the part right here that I just showed, and right here is also epoxied. So effectively, that whole portion becomes one unit, and there's a watertight seal right here and here caused by that adhesive. And if you look very closely, there's a groove for an O-ring to be seated. So an O-ring is like a rubber, like almost like a gasket, where it's placed within this groove. And when we push the hull on, so when we push it in this way, basically the rubber is compressed along with the metal, and it fills sort of like the empty space and creates a watertight seal. So to do that, we have to hit a really reliable tolerances, 0.003 of an inch. So that's why we take our tolerances so seriously and our machining so seriously. So yeah, pretty simple parts so far. SEACON panel, a little more complicated. It also has an O-ring groove, which isn't pictured, but it's on the back sort of. It fits sort of into the mid cap, or in other iterations, like we can go back to here. There's sort of more directly on the side of the cap, and then there's a more proper SEACON panel there. But basically, you know, we have like various numbers of SEACON of different kinds, and there's a washer and a nut on the back. And basically, this portion could have just been included in the mid cap, but to allow ECs to integrate and crimp all the cables more easily, we just do a separate panel with an O-ring that gets compressed onto the side of the mid cap. So just a quick structural recap. In this iteration, which is one of the mid caps we're reusing, here's the mid cap, 2 SEACON panels, 2 collars, 2 hulls, 2 end caps, pressure relief valve. And in this iteration, we actually had an LCD screen, so we could see stuff from above. Just another like thing that we added. So just some like unique features, sort of recapping stuff that I didn't talk about. Sealing, we always use O-rings. Very reliable, very reasonably expensive. Easy to hit the tolerances if you're using a CNC. Manual machining, it's a little bit harder, but still within reason. So we do about 0.003 of an inch, like I said. The UHPV is also vacuumed on each time it's resealed, so that's why we have the pressure relief valve. We pull a vacuum and create like a semi-vacuumed environment inside. So hopefully if there was any leak that actually propagated, the vacuum would cause the water to be pushed out instead of initially pushed in. That's partially why we have this pressure relief valve right in the back. Material-wise, we use aluminum mainly for everything. It's just easy to machine, high mechanical properties, hit the tolerances like I talked about. And acrylic is mainly for serviceability, so we can evaluate the electrical system without opening everything up. It's also cheap, lightweight. Shape-wise, we tend to do like cylindrical hulls. It's hydrodynamic. It's also easy to get the stock. So we can do stuff on the lathe if we have to. We can do stuff on the CNC. And then it also interfaces really well with a circular O-ring. So you can buy O-ring, or you can sort of manipulate O-rings to fit any profile, but they're circles already, so it's easy to size them and fit them with circular O-rings. So that's another sort of motivation for the cylindrical shape. Placement, we try to have them high up, easy to see, remove and assemble. So if I could go back to the CAD, but you know, the hole in the UHPV had a pretty dedicated spot that was, you know, you could pull everything in and out with no obstruction. And then also to balance the SEACON cables, the UHPV is the heaviest and most buoyant enclosure at the same time. So if I go back, you can imagine a big mass of cables here and here, and then these 2 large volumes, which have pretty small mass because they're just mostly filled with air, at least relative to their volume. So these 2 parts are very buoyant right here, and these 2 parts are very heavy. So, you know, making sure our sub is balanced so it doesn't have to have too much trimming or like, you know, weight or foam added anywhere is also kind of crucial to the placement of the UHPV. And then also what we enclose isn't entirely trivial within the UHPV. It kind of varies from year to year, sort of a function of balancing the UHPV's size. The racks always are inside the UHPV and support most of the PCBs. So you can see like this cantilevered portion, which attacks the UHPV, and then the hull would slide on this way. But the computer is also there actually, but things that are like noise sensitive, so that could be like the heading and inertial measurement board, which is in sensor boom motor enclosures, or transmit, which is in charge of inter-sub communication, or hydrophones, which is in charge of pinger tracking. Some of them, so the first one was noise sensitive, so we isolate it in another enclosure. The other two actually have elements which need to be directly in contact with the water. So we also isolate those sort of away from this main structure and connect everything via SEACON connectors. So it's not entirely trivial what we place in there, sort of to optimize the performance of each sensor and component. We place them appropriately. Some future work, we've done some geometry which was not cylindrical. So this is from Pollux and Ajax. This was a UHPV that was used twice. Had its pros and cons, but it was rectangular, also with an O-ring, this time latches. We've also thought about some materials, maybe composites, 3D printing as capability goes up, how we can expand that in underwater applications. And then thermals is something I'm interested in, so heat sinking, maybe fans or other cooling solutions. So it's 2 temperature gradients of our sub, roughly. So thank you so much for watching the video. If you have any questions, feel free to reach out to CUAV leader or BDJ25 at cornell.edu. This one's me, this one's just the general team. Thanks.